Okay, I am here today to bring you the Nernst equation. But first, before we get into Nernst, I think I need to sing you a song about Nernst, as I am so very fond of this equation. Okay, let's give this a shot. When I was younger, so much younger than Faraday, I never needed Nernst to solve a problem anyway. But now my cell has changed and delta G is new. K is Q, what should I do to help me understand? Nernst me if you can, I'm feeling down. And I do appreciate that Nernst is around. Help me get my Nernst back on the ground. Won't you please, please Nernst me? Didn't know your professor was so talented, did you? Okay, Nernst, let's get serious here. This is not joking. We're talking about Nernst, very serious. Okay, so what is Nernst? Nernst, in a nutshell, allows us to calculate a non-standard cell potential. Why do we care? Because if we can manipulate our cell voltage, we might even have a more powerful battery, and that would be cool. Or galvanic cell, if you prefer. So at this point, you know about E-cell, standard, because you use the standard potential, the standard reduction potential of the reduction reaction minus the standard reduction potential of the oxidation reaction, and you can calculate E-cell easy peasy. Okay, so that's one part of this equation. But what is this equation? We're saying that E, non-standard cell potential, equals standard cell potential minus this whole term here. What is this whole term here? This is RT over the number of moles N times the Faraday constant times the ln of Q. What is R? R is the gas constant. What is T? T is the temperature. N is the number of moles transferred in our redox reaction. F is good old Faraday, a constant, 96,500 joule per Kelvin. Also, that's code for a volt. We have Q, our mass action expression, which, as you may recall, is kind of like K, except for the fact that it's almost never equal to K. It represents, by definition, non-standard concentrations. And also that delta G, the amount of useful work that we can do, is not typically equal to delta G naught. Okay, so these are all useful concepts that we're all going to bring together in some kind of gorgeous harmony here in the Nernst equation. All right, so in order to do a problem, we have to have a problem to do. And we're going to look at this balanced redox reaction right here, which is solid aluminum getting oxidized to form, and I should have a little aqueous here if I'm behaving. So solid aluminum getting oxidized to the Al3 plus species, and then aqueous iron getting reduced to solid iron over here. Okay. What's next? Let's take a pause. Let's take a moment to kind of drink all this in. Okay, well, we need all these terms. That's going to be our focus right now. We need something to plug in all these places, given certain non-standard conditions. So for non-standard, if we're going to have a Q, we need to have some concentrations. And I'm going to just kind of give some slightly arbitrary concentrations here. I'm going to say that our iron 2 ion is 1 molar, and that our aluminum ion is 0.1 molar. Okay. How many moles of electrons are being transferred in this here reaction? Well, if you think about it, if aluminum is reduced to Al3 plus, that would be 3 moles of electrons. However, we have these stoichiometric coefficients. So that means we have 2 moles of aluminum being reduced to 2 moles of Al3, and we must therefore take our 2, multiply it times the 3 moles of electrons for a total of 6 mole of electron being transferred away, I should say, from aluminum, and greedily accepted by iron, which is going to get reduced and form the solid. Okay, so our N is 6 moles of electrons. What else? Our R is the gas constant, that's 8.314 joule per mole dot Kelvin. Our temperature is going to be 298 K. Faraday, we already discussed, 96,500 joule per mole dot Kelvin. Joule per coulomb rather. And I think that covers it except for Q. So let's start and ignore Q for the moment. Let's just get everything else in here. Now E equals, but we have another situation here. We don't have E cell naught. Can we get E cell naught? Yes, but we need to know the standard reduction potentials of both aluminum and iron and calculate E cell. So if we do that real quick, like, I gotta find it here. I know I have it. Delay of game. Okay. Aluminum getting reduced is negative 1.66 volt standard potential. Iron getting reduced is negative 0.45 volt standard reduction potential. Who is our big winner? This is iron, Fe 2 plus, and this is aluminum, Fe 3 plus. The winner is, this is a negative here and here, the winner is iron because it's the bigger number. So our E cell potential, E standard cell, is going to equal negative 1.66. Oh, no, wrong. Hang on a second. Negative 0.45. That's the reduction minus the oxidation. So we take the negative of the 1.66, which makes it a plus, and we get an E cell of 1.21 volt. Okay, so we now have this 1.21 to plug in over here. So 1.21 volt equals, let's see if I can hold this down a little. 1.21 volt minus, hate it when that happens, 8.314 joule per mole dot Kelvin times 298 Kelvin over 6 moles of electron times Faraday 9,6500 joule per coulomb. Now we need ln of Q. What is the ln of Q? Well, notice we said we have 0.1 molar aluminum ion, 1 molar iron ion. So we're going to put in what? We're going to put in 0.1. Do not forget we have a stoichiometric coefficient of 2 here, so this has to be squared. And then we put in the 1 molar and cube that because we have the stoichiometric coefficient of 3 here. So now we are really ready to rock and roll. Are you going to make me calculate this, huh? I don't think I should have to. You know, once you get a professor, it's like kind of above your pay grade to have to punch numbers into calculators. That is your job. So I'll make you a deal. If you send me the solution to this, I might give you a point of extra credit on one of your exams. How generous would that be? So it would prove to me any number of things. 1, you know how to punch numbers into your calculator. 2, you took the time and effort to watch this video and you have some understanding of Nernst. 3, I don't know, it's kind of fun. And also it gives me a little more liberty to talk about my prediction for E. So I think it's fair to say that E is either going to be greater than 1.2 volts or it's going to be less than 1.21 volts. If it is greater than 1.21 volts, this reaction has become increasingly spontaneous, and the opposite will be true in the other case. So what would your prediction be based on the fact that we have 1 molar reactant here and 0.1 molar over here? My feeling is that we have a lot of reactant and not very much product. And if we have a lot of reactant here relative to product, that probably means that Q is smaller than K. If Q is smaller than K, it further seems extraordinarily likely that the equilibrium of this reaction, based on Le Chatelier's principles, will be pushed to the right. That would have the effect of making our E cell, not standard, more spontaneous. So my prediction for you is that E is going to be, non-standard is going to be greater than E cell standard. And you can, I don't know, find a way to punish me if I'm wrong. So that's all I have to say about Nernst, and hopefully that was useful.